In this video, we're going to learn about the observation and system model of the Kalman filter. Before we begin with them, let's recap quickly what the objective of the Kalman filter is. Our goal is for any time step n to find the LMMSE estimates of the samples of a process y of n, which we cannot observe directly, from the samples of a related process, which we can actually observe, x of n, obtained up to that time. This means that at any given time n, we aim to find the LMMSE estimate of y of n given the observations of x from time 1 up to that same time n. The Kalman filter, however, is not just an LMMSE estimator, but is a recursive LMMSE estimator. Therefore, we need to find a recursive implementation of the estimator. This means that at any given time, say time n plus 1, our LMMSE estimate of the process y at that time is going to be obtained as simply a linear function of the LMMSE estimate of y at the previous time, in this case y of n, and the newly obtained observation of x of n plus 1. As we will see, it turns out that this recursive implementation can only be obtained when the processes y and x are defined appropriately. So in this video, we will examine how we model the unknown process y of n, which we want to estimate, and how we model the observable process x of n, from which we will obtain the estimates of y. In this slide, we can see the block diagrams of the system and channel models used in the Kalman filter, as well as the block diagram of the Kalman filter itself at the bottom. For the time being, we will focus on the top part, and we will discuss the Kalman filter in a later video. If we look at the top diagram, on the left-hand side we have the system model. The system model illustrates how each sample of y of n is related to previous samples of the process. What we can see in this diagram is that the sample of y at time n will be made of a weighted version of the previous sample of y of n minus 1, which is weighted here by a constant h of n, to which a noise process will be added. As I said before, we cannot observe the process y of n directly. Instead, we observe it through what we call the channel model. The channel model here exemplifies how each of the samples of the observable process x of n are generated from the samples of the unknown and non-observable process y of n. As we can see in this diagram, each sample of x is generated by multiplying the same sample of y at the same time n by a constant a of n, and then by the addition of a noise process w of n to it. So each of the samples of x is a weighted and noisy version of the samples of y. As we can see in these two diagrams, the samples of the observable process x of n will actually constitute the input of the Kalman filter, and at the output of the Kalman filter we will obtain the linear minimum mean squared error estimates of y at that time n. Let us now have a closer look at how the system model is defined. So, based on this block diagram, we can actually write what we call the state equation for the process y of n. We can say that at any given time, the sample n of a process y will be made of the multiplication of a given constant h of n with the previous sample of y of n minus 1, plus a sample of a noise process z. If we try to define each of the elements that shows up here, we have that h of n is going to be a deterministic and known sequence. So we're going to assume that we know how much each of the samples of y depends on the previous sample. via the sequence h of n. Now notice that the sequence h of n has here a index indicating the dependency on time. This means that although the sequence is deterministic and known, it could be that these weighting coefficients change at each time, but they will do so in a deterministic and known way. Second element we have is the noise process z of n. Z of n is assumed to be white noise with a given variance that can also be dependent on time, and this is why we indicate it as sigma z squared of n. What does it mean that this process is white noise with possibly time-varying variance? Well, it simply means two things. The expectation of the process z of n, its mean, is going to be equal to 0. And the autocorrelation of z of n with another sample with time shift k is going to be only non-zero when k is equal to 0, and it's going to be having a value sigma z squared that it can be possibly depending on n. We just lack one more thing to define here, which is, since the process y we assume it to start from time 1, 2, and so on, we need to define what is the starting condition for the process y, meaning we need to define how y of 0 is distributed. And at the moment we will only assume that y of 0 is in principle a random variable, and this random variable will have a known mean, which will denote mu of y0, and a known variance sigma squared of y0. Let us now have a closer look at the right-hand side of this block diagram at the channel model. The channel model tells us how the samples of the observable process x depend on the samples of the unknown process y that we want to estimate. As we can see in this diagram, each of the samples of x is observed by a weighted version of the sample nth of y, which is weighted by a coefficient a here, and to which some noise process w of n is added. Maybe it becomes a bit more clear if we look at it in the following channel equation, in which again each sample of x is a weighted version of the corresponding sample of y, to which the corresponding sample of the noise process is added. Let's have a look at the different elements that are in this equation. First, the sequence a of n, similarly to the free sequence h of n before, is a known and deterministic sequence. Again, the weights a here may change with time, but they will do so in a predictable manner, meaning the filter, the Kalman filter, will have knowledge of this sequence. The noise process w of n is similarly defined as the other noise process z of n here. It is a white noise process with a variance that can also change with time, sigma w squared of n. Similarly as before, this again means that the expectation of the process w of n is going to be 0 for all time steps, and the autocorrelation of two samples of the process is only going to be non-zero when k is equal to 0, so only the same sample will be correlated with itself, and the value of this correlation will be given by the variance of the process, which in principle can change with time. Now, to finish, we just need one more element, which is to define how the different random variables and processes involved in this block diagram relate to each other. For the Kalman filter, we only need to assume that the initial state of the unknown process y of 0, all the samples of the system noise process z of n, and all the samples of the channel noise process w of n are mutually uncorrelated. In the following videos, we will see how the Kalman filter utilizes all the assumptions made on the system and channel model in order to implement a recursive linear minimum mean squared error estimator of the samples of y at any given time n, given the observation of all the samples of x from time 1 to that same time step n.